A baseball player hits a home run and the ball lands in the stands 7.5 meters above the point where it was hit. It lands with a velocity of 36 meters per second at an angle of 28 degrees below the horizontal. Ignoring air resistance, find the magnitude and direction of the initial velocity with which the ball leaves the bat. So first off again, let's identify our variables with our knowns of what we know and draw a diagram. Okay, so we have a diagram here, the baseball player hitting the ball, some initial velocity of which we don't know. We don't know what angle either. Okay, launches it up, it lands in the stands, he hits a home run, but it's actually 7.5 meters above where he actually hit the ball from. So I've tracked that as my vertical displacement. The final position ended up 7.5 meters above where it started. Again, we could plug in our accelerations of 0 and negative 9.8 meters per second. We know that the ball lands here with a final velocity of 36 meters per second, and it is at an angle that is negative 28 degrees. Okay, negative 28 degrees or 28 degrees below 0. So again, we have information that's coming in two different planes. We need to break that up into our horizontal and vertical components. Okay, so we solve for each of our components. Again, the horizontal velocity component is going to be the velocity component times the cosine of theta, which solves for 31.786 meters per second. And the vertical component, again, is going to be v, the actual velocity vector, times the sine of the angle. So plugging in, we get negative 16.9. Again, looking at this in the vector addition of tip-to-tail method, we're told 36 meters per second, 28 degrees below the horizontal is what the ball actually hit the stands with. And then what we've broken it down into is the horizontal and the vertical components. So that can get plugged back into here in the final. Okay, so horizontal is 31.786. And we know that is consistent throughout. So we can plug it in for both the initial and the final velocities. And the final vertical velocity is negative 16.9 meters per second. So we've broken these up, and ultimately we're trying to solve for this the initial velocity, which I need to know my vertical initial velocity. So I have three variables. I could go ahead and solve for my initial vertical velocity, so let's go ahead and do that. Okay, so we did not know time, so I needed to find final velocity with an equation that does not have time, which gives us this equation. The final velocity in the vertical square is going to equal the initial velocity in the vertical square plus 2 times the acceleration in the vertical direction times the displacement in the vertical direction. Well, reworking this equation, I move over the minus, subtracted both sides by 2 times the acceleration times the displacement is equal to the initial velocity squared. So I move this over, and then I knew I had to take the square root of both sides. So I rearranged the equation in variable form, and then here I'm actually plugging it in, where the initial velocity in the vertical is going to be the square root of negative 16.9 squared, that initial velocity, minus 2 times the acceleration in the y, negative 9.8, times the displacement in the vertical, which was the 7.5 meters. Taking the square root of the whole thing gives me an initial vertical velocity of 20.8 meters per second. So now I have both the horizontal and vertical components of my initial velocity. I can use Pythagoras Theorem to go and solve for first the magnitude, and then I'll use trig to solve for that angle. Okay, Pythagoras Theorem. Rearranging, plugging in for horizontal and velocity, vertical and horizontal components, squaring, taking the square root, we'll find that the actual velocity is 37.9867 and change meters per second with 3 significant figures. That's going to give us 38.0 meters per second as the initial velocity of the ball. That's how fast the ball is coming off the bat. And now we just need to find the angle. And so we'll use our vector addition and our trigonometry to find that. Okay, just drawing our vector diagram to point out the relationships. Again, you have a vertical initial velocity component, a horizontal initial velocity component. We can move our vertical over and use the tip to tail method to create our right triangle. And we can see that I could use any one of the trigs, sine, which would be opposite over hypotenuse, or cosine, which would be adjacent over hypotenuse, to solve for that angle, but we're going to use the tangent function, opposite over adjacent. Then we're going to take the inverse tangent of opposite over adjacent to solve for the angle in degrees. So theta is equal to the inverse tangent of 20.8 divided by 31.786, which gives us an angle of 33.2 degrees. So the final complete answer to the question is that the ball was launched at 38.0 meters per second at an angle of 33.2 degrees above the horizontal.